Yes, so what I'm going to talk about is it's a problem in quantum mechanics and the solution of it through analysis and probability. And this is based on joint works with Mitja Petrake, who's in Chile. Now, when I first decided to talk about this, I have to tell you I was quite nervous, because obviously you look at the title and you think, what has it got to do with data science? Of course, probability has a lot of things to do with data science, so it is the fundament on which statistics is based and as such is necessary to data science. So in our department, in the statistical science department in UCL, so we have a fresh MSc in data science, well, fresh, 2 years new. And one of the things that we have two core modules that we teach. One is an introduction to statistical data science, which is half probability and half statistics, and introduction to machine learning. So you can easily argue probability in data science. However, quantum mechanics, well, at first sight, it doesn't seem so easy to argue. So in a way, I was quite grateful for the morning talk of Noor, where she used quantum mechanics quantum mechanics played quite an important role in the application to data science. Now, what I'm going to try and argue for you now in the first slide, I'm going to try and argue for you why quantum mechanics is quite useful in data science, and also why you can use data science tools and statistics tools in quantum mechanics. And after that, I will go into the math and the theory behind, and then come back to the statistics at the end. Now, of course, quantum mechanics is really, really cool area of science. I think it's very cool. And it has lots and lots of applications. There's the obvious ones, so quantum computing, quantum chemistry. Of course, there's other applications. So, for example, superconducting magnets, lasers, transistors and semiconductors, medical and research imaging, lots and lots of applications. So lots of biological and physical phenomena can be explained to quantum mechanics. However, there's also increasing interactions between quantum mechanics and data science. So if you Google quantum mechanics and data science, you're going to find lots and lots of articles about how they say that computer processes, such as, for example, quantum computing, are going to revolutionize data science and how they are going to be really, really useful in big data. Of course, until quite recently, this was just a theory, but in December 2017, IBM announced that they had created a quantum computer. NASA now have a quantum computer, so it's all starting to become a bit more real. Now, what are the two important properties from quantum mechanics that quantum computing is using? One of them is superposition, and one of them is entanglement. Now, what is a superposition? So particles can be in several states at once. What is entanglement? It means that particles can interact with each other even if they are at very large distances. And for quantum computing, this is very useful because it means that a quantum computer can run a large number of operations at the same time. And if you look on Google to try and find applications, so there's quite a increasing number of articles where they are trying to use quantum computing. So, for example, there's a new research by MIT, University of Waterloo, and Southern California, where they are using quantum computing and quantum mechanics for topological data analysis. Later on, towards the end of the talk, you are going to see how you can use topological data analysis for the quantum mechanics problem. So it goes the other way around too, which is quite cool. At least I think it's really cool. There's also new research. There's also research in progress by NASA and D-Wave, and they are trying to use quantum computing for space exploration. And for a number, so if you look on the website, so they say that they are trying to use it for clustering schemes and for data fusion and multi-label classification and a lot of other quite interesting things. So, of course, this is the way that you can try and use just part of quantum mechanics to big data. There's also the other way around. So you can try to use data analysis tools to quantum mechanics. So this is quite new, and it's only started in the last few years, but people are now starting to use machine learning techniques in quantum mechanics to try and speed up. So that, as you will see a few slides later, there's quite high computational cost in quantum mechanics, and machine learning techniques are starting to become quite useful and quite helpful in simplifying these computational costs and in obtaining more reliable results. There's, of course, a third possibility where you can use both quantum mechanics and machine learning tools to solve other real-life problems. And this has already started to be done for the Higgs boson. Now, just last but not least, computational chemistry, where quantum mechanics is heavily used. It's a big generator of big data. And that's where quantum mechanics plays quite an essential role. So there's a lot of ways in which you have interaction between quantum mechanics and big data. And there will be some more later on. Okay, so now I'm going to tell you a bit about how probability appears in quantum mechanics and how it plays a very central role in quantum mechanics. So in classical physics, of course, probability plays a role, and it enters when you have incomplete information about a system. However, in quantum mechanics, probability theory is essential. To begin with, some physicists were not quite happy about this, and that was including Einstein, and they kept hoping that there will be eventually a deterministic theory that will be found. Einstein even expressed his view by saying God does not play dice. However, probability theory plays a very important role in quantum mechanics. So one very simple way in which this happens, so we're always talking about electrons, and this really means we're talking about the probability that an electron is in some infinitesimal place in space at any given time. So we're always going to work with these probabilities that the electrons will be found in space at some given time. However, much more delicately, and this is where things start to become complicated, is that you have the interactions between electrons playing a role. So you're always going to try and understand correlations. And we're going to try and understand what are the correlations between different electrons and how they interact with each other. And there's a lot of effects where you have these correlations: entanglement, crystallization, phase transitions. Phase transition meaning you're trying to see when a system goes from a phase to another. So, for example, water, and phase transition from water to ice at 0 degrees, or water to vapor at 100 degrees. So these are phase transitions. And all these types of quantum mechanics properties, so entanglement, crystallization, phase transitions, they have correlations and they have such probabilistic type behavior. Okay. Analysis also plays a big role, and my pretty amazing analyst collaborator, Mitra, he would be able to tell you a lot about it, but I'm not going to mention anything about it today. So I'm going to now give you a very informal introduction to quantum mechanics. Just very basic. Now, I'm not a quantum physicist, I'm a probabilist, and I got into this 10 years ago, into working on quantum mechanics 10 years ago. So I was doing a postdoctoral fellowship in Munich, and I got to talk to some people who were working on quantum mechanics, and I thought the problems were really cool. So I started working with them on the topic, and then I continued to work on it. So let me tell you a very little bit about quantum mechanics. So what we have in nature, we have material systems, and they all consist of electrons and nuclear charge. Yeah? And all these systems have properties. They have a lot of properties, mechanical, electronic, magnetical properties, and all these properties are due to electrons and to the way they interact with each other. And what we use in order to define and explain this interaction is Schrodinger's equation. Now, of course, this equation allows us to predict lots of many important properties, such as, for example, bending energies, equilibrium geometries, intermolecular forces. And if I were to reduce Schrödinger equation to something easier to understand, so I could reduce it to a partial differential equation. So this is Schrödinger's equation. And it's for a function psi, I'm going to call it psi, on R to 3n, so lives on a very large space. Psi is what was in the morning talk called the wave function. And this is basically the solution to this Schrödinger's equation. R to 3n is a very big space, as you will see later on, because so n represents the number of electrons. And usually we're going to have a system with a very large number of electrons, so this is going to be a really, really big space indeed. Okay. So psi is the wave function and represents the state of the m-particle system. And it depends on the number of electrons, n, and on the positions of the electrons. So for each electron I have a position, xi. Now, the wave function has a really cool property. So if I take its absolute value and I square it, it becomes a probability density. And it's the probability that each electron I is at position xi. Now, psi has some really nice properties from a probabilistic point of view. So it is an antisymmetric function, which means that its absolute value squared is a symmetric function. So what does it mean that it's a symmetric function? So it means that so for example, a standard normal distribution is a symmetric function. So if I were to rotate it, for example, around the vertical axis, it will keep its value. So it's from a probabilistic point of view, symmetry is a very nice property because there are a lot of tools that one can use and that both probabilists and statisticians use when you have nice symmetry on your probability measure. Now, as we've seen before, so we've seen on previous slide, we have the Schrödinger equation. And what we would really like, we'd like to solve it. If we could solve it, then we'd be able to know almost any property of the materials and of the systems. Problem is, we can't solve it. And there is no method currently available to give us accurately the solution. However, there have been some methods which have had increasing success over the years. So one such method is called density functional theory, shortened to DFT. So we can't solve this big Schrödinger equation. We cannot solve it analytically. So this is where you start doing, there's a way to try and do simulations. You have a very big space, curse of dimensionality. So remember, we are working in R to 3n. Just to take up something with really few, let's take a carbon atom. It has n equals 6. That's small, yeah? Remember, we had R to 3n. Well, in this case, it will be R to 18. It's a lot. We can discretize R. Let's discretize it by 10 points, and that gives us 10 to 18 grid points. That's quite a lot of computational effort for just something with 6 electrons. In real nature, we are going to have a lot more electrons than that. So what we're going to try and have to do, we're going to try and do approximations. And this is what density functional theory allows to do. So it's a simplified version of quantum mechanics. And this is quite widely used in chemistry simulations, in physics, and in material sciences. And what's the main idea? So have a very large, complicated system with many particles, with m particles. As we've seen, it lives on a very, very big space, R to 3n. And what we would like to do, we would like to bring it to a much lower dimensional space. And what we would like to use, we would like to use the density of each electron. So each electron, we said that there is a probability that it will be at some particular point in space at any given time. And that probability, so that density is called rho. And you can find it, so if I take the wave function, and I take its absolute value squared, and I integrate it with respect to all its variables apart from 1, that gives me the single particle density. And this lives just in R3. So much lower space, R to 3n, R3. And what we would like to do, so what density functional is trying to do, is trying to describe the system instead of using the one with R to 3n electrons, to use the one just to R to 3. Yeah? R to 3 space, much lower space. So just before I tell you more about it, so let me give you a bit of history about DFT. So the first time when it was encountered, so it was encountered by Thomas and Fermi in 1920. It was a very simple model, and it was based on the fact that there's some okay, all particles are independent. Not very good, but it was the starting point for all that followed. Later on, Hornberg, Kohn, and Schramm, they devised some practical methods based on approximations of rho. They are called semi-empirical functions. Then later on, in the late 90s and early 80s, there was a mathematical justification and reformulation of the Schrödinger equation by Levy and Lieb. It started to become popular in the 1970s. It was not accurate still, but in the 1990s, there was a big explosion in computational chemistry due to the increase of computational resources, and there were a lot of approximations based on the single electron density rho. Okay. Just a couple of fun facts before we move on. So if you put in Google density functional theory, so if you in Google Scholar density functional theory, you are going to see there's more than 15,000 papers per year with this keyword. It's really big business. Now, if you Google also, so if you Google which is the most cited physicist, again, Google Scholar, the most cited physicist of all time. So John Perdue, who's a designer of density functional theory models. So as of yesterday, he had 2,985 citations, and it was almost double as the number of citations for Einstein, yesterday's citations. So very big business. Okay. So what's the key quantum mechanics quantity that we're interested in? It's the ground state energy. And ground state energy is taking the infimum after all these wave functions of some energy functional E, which depends on three quantities. T is kinetic energy, VEE is electron-electron interaction, and VNE is electron-nuclei interaction. Now, it's not a very pleasant-looking formula. It's quite ugly, so it's not on the slide. There is a simplified reformulation of this that was done at the end of the 70s, so the Hornberg-Kohn-Schramm model. So what Levy and Lieb did, so they reformulated it in terms of the single electron density rho. So instead of rewriting the infimum after this wave function, which lives on the big R to 3n space, they rewrote it in a pretty form so that it looks like the infimum is just after the rho, which lives in R to 3. However, it's deceptive because if you look carefully at the formula, you will still find the big R to 3n space. So the wave function is still there, but it is hidden. So it doesn't help in any way if you're going to try and do computation, if you're going to try and do computational approximations. However, it's a good starting point for this. And let's look at the mathematical structure that you get when you end up with this reformulation. So you have an approximate energy functional. So you have the energy functional E of rho, which depends on this electron density rho. However, if you are going to look at the formula, you are going to need to understand the correlation structure. So you are going to need to understand how the electrons interact with each other. And I'm going to call this the density of the interaction between electrons, ρ2. However, we are not going to know what is this ρ2, because in order to know the ρ2, we'd have to solve Schrodinger's equation. And we cannot solve this. We do not know how to solve it. So what density functional theory does is trying to guess in a way what is the form that ρ2 has, and develops various models to try and tells us what ρ2 is as a function of just a single electron density ρ. And the standard way, so is start by assuming independence, so this is called mean field in physics, and then add various corrections to account for correlations. And this has sometimes accurate, often it's accurate, but it's not always reliable. So always you have start by the independence, the mean field plus correction. And let me give you a couple of ones. So the first one coming from the Thomas Fermi in the 1920s. So just assume independence. Then ρ2 is just, if I have independence, I have a product measure. So what I would end up is just with a product measure. Local density approximation is more complex. So I'm going to have the product measure minus some correction term to account for correlation. Okay. These are just two of many, many possible such approximations that exist in density functional theory. So some of them have many, many terms. I've seen some with 43 terms. So these are just two very simple ones. So let me now come back to a new mathematical approach in which one can use a combination of probability theory, analysis, and statistics to try and say something new that will help about the original density, about the original quantum mechanics problem. And let me tell you a bit about what optimal transport is before I'm going to tell you what we do. So optimal transport is a very popular area in analysis that many great mathematicians have worked in, such as Villani, who is a Fields medalist. Now he has a book where he gives a very nice example of optimal transport using bread. Now I like cakes, so I'm going to give you an example of what optimal transport is using cakes and bakeries. So suppose all the bakeries, so suppose I have a set of bakeries in London, and suppose we're in a really sad world where all these bakeries are doing the same cakes. And we know how many cakes each bakery produces, and we know how many cakes are required from each bakery. And suppose we want to transport the cakes from these bakeries to some restaurants, and we want to do it in an efficient way. Yeah? So if I know how many cakes are produced, I'm going to have a density for this case, a density of production, and I have a density of consumption for how many cakes are needed to be consumed every day. And I said I want to do this in an efficient way by fixing this density of production and density of consumption.
Can you please finish in 2 minutes?
Oh, in 2 minutes?
Yes, just with some conclusions.
Okay. All right. Okay. So what you can do, so in work with the experts from Munich, what we were able to do, so we were able to say that one of the terms appearing in the Hornberg-Constant formulation, so you can write it, so you can rewrite it, you can reduce it to an optimal transport problem. And this is a completely new form. It keeps the correlation structure of the measure, so it allows us to find a ρ2, to find the ρ2 with a good correlation measure. And then, of course, to find it explicitly, this is where we need to use topological data analysis. So this is what part of the work that Mircea Petroic and myself are trying to do. So we're trying to look at the optimal configurations. And in order to do that, it turns out it's quite useful to use topological data analysis. And then some other things you can look. We can try to understand how this optimal transport problem behaves for large n, and we can, if we do so, we can recover the mean field functional, and we can also look at the energy which is not encoded in the mean field functional, and that allows us to say something more about the constants that should be put in the local density approximation. And then also one other tool that we can use is copulars from statistics. We can also use various tools from analysis. And I'm going to stop here, and I'm going to leave you with citations from quantum mechanics. Thank you.